The universe operates on a set of very strict, very predictable rules. We call these the laws of physics and the principles of planetary formation, based on everything we have learned from observing thousands of star systems. A gas giant simply cannot exist right next to its host star without being evaporated into nothingness. Rocks aren't supposed to rain from the sky in molten sheets, and planets certainly aren't supposed to be older than the stars they orbit. But somewhere in the deep, ink-black void of the Milky Way, there is a world that defies every single one of these rules. It is a cosmic middle finger to every textbook in our libraries. Today we are traveling 500 light-years away to look at a world that mathematically and physically should not be able to exist. Yet it sits there, spinning in the darkness, waiting for us to figure out how it cheated the odds. To understand why this specific planet is such a headache for astronomers, we first have to look at the standard model of how a solar system is born. Imagine a massive cloud of gas and dust called a nebula. Over millions of years, gravity pulls this material together until the center starts to glow, becoming a protostar. Around this young star, the remaining dust and gas flatten out into a spinning disk. In the inner parts of the disk, it is too hot for gases like hydrogen and helium to condense, so small, rocky planets like Earth and Mars form there. Further out, beyond what scientists call the frost line, it's cold enough for those gases to clump together into giants like Jupiter and Saturn. This is how it's supposed to work. Hot rocks near the star, cold giants far away. But then, we discovered Hall of Fame rule breaker number 1. The planet known as Hala, orbiting a star called Baekdu. Now on the surface, Hala looks like a typical gas giant, somewhat similar to Jupiter. The problem isn't what it is, but where it is and how it survived. You see, its star Baekdu is an elderly red giant. Long ago, this star ran out of hydrogen fuel and began to swell to an enormous size. Based on our calculations of stellar evolution, Baekdu should have expanded so far that it would have completely engulfed Hala, incinerating it in a matter of hours. Yet after the star shrunk back down to its current size, the planet was still there, sitting exactly where it should have been consumed. It is like finding a perfectly intact ice cube sitting inside a roaring fireplace. How is this possible? If the star expanded past the planet's orbit, the friction alone should have dragged the planet into the star's core. Some scientists suggest that Hala was saved by a cosmic game of musical chairs. Perhaps Baekdu wasn't always a single star. If it was originally 2 stars that merged together, the merger might have fundamentally changed the way the star expanded, allowing the planet to dodge the fiery embrace of its parent. Or maybe Hala is a second-generation planet, born from the debris left over after the star's violent expansion phase. Either way, it shouldn't be there, and its existence forced us to reconsider every timeline we have for the life cycle of planetary systems. But Hala is just the beginning. The deeper we peer into the universe with telescopes like James Webb, the more we find worlds that seem to be glitches in the simulation. Consider the environment of a hot Jupiter. These are massive gas giants that orbit their stars in just a few days. They are so close that their atmospheres are heated to thousands of degrees. According to the laws of thermodynamics, a gas giant that close should be losing its atmosphere at a rate that would turn it into a tiny, naked core in no time. Yet we see them and they stay puffy. They shouldn't exist because they are too massive for their location and too stable for their temperature. Then we have the worlds that are so dense they defy the gravity of their own formation. There is a planet called K2-141b, often referred to as a lava world. This place is so close to its star that one half of the planet is a permanent ocean of magma, while the other half is locked in eternal darkness. Because of the extreme temperature difference, the rock literally evaporates into the atmosphere, travels to the dark side, and rains down as solid stones. While a lava planet is possible, the atmospheric dynamics of K2-141b are so extreme that the planet's surface is constantly being reshaped in a way that suggests it should have disintegrated long ago under the tidal forces of its star. Let's talk about the impossible ages of planets. In our solar system, the sun was born first, and the planets followed shortly after. But we have found ancient worlds, some dating back nearly 13 billion years, almost as old as the Big Bang itself. Back then, the universe didn't have many heavy elements like carbon, oxygen, or iron, because those are forged inside stars that have to live and pass away before the next generation of planets can use them. A planet born in the early universe shouldn't have enough stuff to form. It's like trying to build a skyscraper when the only material available in the entire world is a single bag of sand. And yet there they are, orbiting ancient stars, proving that the universe was building complex worlds much earlier than we ever thought possible. One of the most mind-bending examples is the planet orbiting a pulsar. Pulsars are the remains of massive stars that went through a supernova explosion. This explosion is one of the most violent events in the cosmos, releasing more energy in a second than our sun will in its entire 10 billion-year life. Any planet orbiting a star that goes supernova should be vaporized instantly or kicked out of the system at thousands of miles per hour. But in the 1990s, we found 3 planets orbiting the pulsar PSR B125712. These were the first exoplanets ever confirmed. Think about the irony. The first planets we found outside our solar system were orbiting a remnant that should have destroyed them. They are essentially zombie planets, existing in a place where life and matter should have been erased. Science is often about finding the average and the expected, but these impossible worlds are the most valuable tools we have. They are the anomalies that prove our theories are incomplete. When we find a planet that shouldn't exist, it's an invitation to dig deeper into the math. Maybe our understanding of gravity is slightly off at extreme scales. Maybe gas can condense in ways we haven't reproduced in our labs. Every time a planet like Hala or the pulsar planets is found, it's like a puzzle piece that doesn't fit the picture on the box, which usually means the picture on the box was wrong to begin with. Let's look at the concept of tidal locking. This is when a planet's rotation matches its orbit, so one side always faces the star. While this is common, we have found planets that are tidally locked so closely to their stars that they are being stretched into the shape of a football. This is the case with WASP-12b. The gravity of its star is literally stripping the planet of its mass, pulling it into a teardrop shape. By all accounts, this planet shouldn't last another few million years, which is a blink of an eye in cosmic terms. The fact that we are seeing it right now is statistically improbable. We are witnessing a world in its final moments. A brief transition that defies the long-lived stability we expect from planets. And then there are the rogue planets. These are worlds that don't orbit any star at all. They wander through the freezing darkness of interstellar space, completely alone. If a planet is formed from the disk around a star, how can it exist without one? We think most rogue planets were kicked out of their original systems by gravitational tugs of war between other large planets. But some rogue planets are found in places where no stars have ever formed. This suggests that planets can actually form the same way stars do, by the direct collapse of small gas clouds. This would mean that planets aren't just the offspring of stars. They can be independent entities, born in the dark, surviving without a single ray of sunlight. The chemistry of some of these worlds is equally impossible. Astronomers have found signs of a diamond planet, 55 Cancri E. This world is twice the size of Earth, but has 8 times its mass. It's believed that at least a third of this planet's mass is pure diamond. In a universe where carbon is common but not usually that concentrated, a world primarily made of diamond shouldn't have enough pure carbon in one spot during its formation disk phase to become a reality. It challenges our understanding of the chemical distribution of elements in the nebula that creates solar systems. Consider the forbidden planets. These are worlds located in what scientists call the Neptune Desert. We have found plenty of small rocky planets close to stars and plenty of huge gas giants. But for a long time, we found almost nothing the size of Neptune in close orbits. It was assumed that a Neptune-sized planet was the wrong size. It wasn't big enough to hold onto its gas against the stellar wind, but it wasn't small enough to avoid being dragged in by gravity. But then we found TOI 849b. It's a planet that has the mass of Neptune but almost no atmosphere. It is a massive, naked rocky core. It shouldn't be possible for a core that big to exist without gathering gas and becoming a giant. It's like a skeleton walking around without any muscles or skin. It's an anatomical impossibility in the cosmic sense. What about planets in multi-star systems? We used to think that the gravitational chaos of 3 or 4 stars would make it impossible for any planet to maintain a stable orbit. It would be like trying to balance a marble on a vibrating plate. But we have discovered worlds like those in the Centauri system or those orbiting circumbinary stars, Tatooine-like worlds with two suns. Some of these are in triple star systems where the gravity is so complex it looks like a chaotic mathematical equation. Yet these planets found a stable niche. They exist in a state of precarious balance that suggests the universe is much more forgiving of orbital instability than our computer models predicted. The temperatures on some of these worlds defy the logic of distance. Usually, the further you are from your star, the colder you get. But some planets have anomalous heating. They are much hotter than they should be based on the light they receive. This is usually due to internal friction caused by the star's gravity pulling on the planet's core, a process called tidal heating. But in some cases, the heating is so extreme that the planet is glowing with its own light, nearly becoming a star itself. Where do we draw the line between a very hot planet and a very small star? The brown dwarfs occupy this gray area, but finding a world that is clearly a planet by mass but a star by temperature is a paradox that keeps researchers up at night. Even the way we detect these planets is a testament to how impossible they are. Most exoplanets are found using the transit method, watching for a tiny dip in a star's brightness. This dip is often less than 1% of the star's total light. Trying to find an impossible planet this way is like trying to spot a mosquito flying in front of a stadium floodlight from 3 states away. The fact that we can even see these anomalies, let alone analyze their atmospheric composition using spectroscopy, shows that our technology is catching up to the universe's weirdness. We are now able to see the colors of the sunset on these impossible worlds, and often those colors are hues that shouldn't exist in a standard atmosphere. Water is another point of contention. Water is supposed to be the Goldilocks substance, only liquid in a very narrow range of temperatures and pressures. But we have found water worlds where the entire planet is a deep ocean, hundreds of miles deep. Under the crushing pressure of these depths, the water might turn into sea-hat ice, a state of matter called Ice 7 or Ice 10. This is ice that remains solid even at temperatures of hundreds of degrees. A world made of hot ice is a thermodynamic nightmare. Yet the signatures we get from these ocean-shrouded exoplanets suggest they are common. If impossible states of matter like hot ice are common, then our definition of a normal planet is merely a local bias based on our own cozy solar system. We also find worlds orbiting red dwarf stars. These stars are small and cool, but they are incredibly active, prone to massive flares that can strip a planet's atmosphere in a few thousand years. A habitable planet around a red dwarf shouldn't be able to keep its air. Yet we find systems like TRAPPIST-1 with 7 Earth-sized planets, some of which may still have atmospheres. Is there a geological process we don't know about that constantly replenishes the air? Or have we underestimated the power of a planet's magnetic field to shield it from its sun's rage? Every answer leads to 3 more questions. The most profound realization from finding these impossible planets is that we are likely living in a universe that is teeming with variety far beyond our imagination. We used to think our solar system was the gold standard. We have 4 small rocky planets, an asteroid belt, and 4 giants. We thought this was the correct way for a system to look, but it turns out we might be the weird ones. Most systems we see are chaotic, crowded, and violent. We might be living in an unusually quiet corner of the galaxy. Our Meemel might be the universe's exception. Think about the gas dwarfs. These are planets that are smaller than Neptune but still manage to wrap themselves in a thick layer of gas. According to standard physics, they should have lost that gas to space because their gravity is too weak to hold on to it. Yet they sit there puffy and light. They are a contradiction of gravity and thermodynamics. We call them sub-Neptunes, and they are the most common type of planet in the galaxy. And we don't even have one in our own system. This means the most common type of planet in the universe is one that, for decades, we didn't even think could exist. The more we learn, the more the term impossible starts to sound like undiscovered physics. The universe doesn't make mistakes, it only follows rules we haven't fully documented yet. When we see a planet like Hala that survived a red giant's expansion, it isn't a glitch. It is an indication that our models of stellar expansion or orbital migration are missing a variable. Maybe the magnetic fields of stars can push planets out of the way before the heat hits them. Maybe the interaction between the planet's own gravity and the star's atmosphere creates a bubble of safety. We are like detectives looking at a crime scene that looks impossible, knowing there must be a clever explanation we just haven't spotted. Space is not just a place. It's a laboratory of extremes. Everything that can happen will happen somewhere in the infinite span of the cosmos. If life can exist in the crushing depths of our own oceans near volcanic vents, Who is to say it couldn't exist in the ice 7 layers of a water world, or in the temperate zones of a tidally locked lava planet? The existence of these impossible worlds expands the habitable zone of our imagination. If a planet shouldn't exist but does, then maybe our definitions of what makes a world alive are also too narrow. As we look up at the stars, we have to humble ourselves. The tiny sapphire we call Earth is just one expression of an infinite variety of planetary architecture. There are worlds made of glass where it rains horizontally at 5,000 miles per hour. There are worlds where the sun never sets, and others where it never rises. There are worlds that survive the death of their stars and worlds that are older than the stars themselves. Each of these is a testament to the resilience of matter and the complexity of gravity. The only planet that shouldn't exist is the one we haven't found a way to explain yet. This constant search for the explanation is what drives astronomy forward. It's what led us from the idea of a flat Earth to the discovery of these distant, glowing paradoxes. We are a small species on a small planet, using mirrors and math to understand worlds that defy the very logic we use to find them. It is perhaps the most exciting time in history to be looking at the sky, because every new data point from our telescopes has the potential to break our reality and replace it with something even more impressive. The universe is much stranger than we are allowed to imagine. It is a place of beautiful chaos and impossible stability. From the diamond-crusted cores of super-Earths to the zombie worlds of the pulsars, the galaxy is a gallery of the improbable. We are just beginning to walk through those halls, and the most impossible worlds are likely still out there, waiting in the darkness for the light of our telescopes to find them. The story of planetary formation is still being written, and each of these rule-breaking worlds is a new chapter that says, "You think you know how this works? Watch this." It's a reminder that we should never get too comfortable with our knowledge. The moment we think we have the universe figured out, it shows us a planet like Hala or a gas giant in the Neptune desert, and we are back to the drawing board. This is the beauty of science. It is a self-correcting journey toward the truth, fueled by the wonder of the impossible. So, next time you look up at the night sky, remember that among those points of light are worlds that shouldn't be there, spinning in defiance of everything we thought we knew. And in that defiance, we find the next great frontier of human understanding. The universe is big, but our curiosity is bigger. And as long as there are impossible planets to find, we will keep looking.